I'm greeting you, and I welcome you to the second day of Cal Data Science School. And today, chairman will be Oleg Feya. I'm working in Cal, and Yana Lazarenko. She is student in Cal. And today we have four lectures, and we will start from the lecture of Olexandr Isayev. Olexandr Isayev finished. Olexandr Isayev is associate professor at Carnegie Mellon University. He was born in Dnipro and finished and got his master degree in chemistry in Dnipro National University. And then he got PhD in theoretical chemistry in Jackson State University. And now he works at Carnegie Mellon. So Alexander is a great specialist in theoretical computational chemistry and the machine learning methods in this field. So in drug design, drug discovery, substituting DFT with machine learning methods. And his lecture is dedicated to this topic. So Alexander, and now it's Alexander in US, and it's like 2 a.m. at his location. So I'm very thankful for you in so extreme conditions that you joined us and will give a lecture.
Okay, thank you, Oleg. It's a pleasure to be here. First of all, I really like to apologize that I couldn't make it yesterday. Yana, would you please unshare the screen?
One moment, I forgot. So you saw this QR code. You can ask your questions in Slido program, and we will send the link to Slido in chat.
So I was just sending the link, so you can use the link or QR code as you wish.
Okay, let's get started. Good afternoon, everyone. So today I'd like to talk a little bit about some of the direction what my lab is doing in combining computational quantum chemistry, quantum mechanics, and machine learning and AI. Before I run out of time, so first of all, let me acknowledge all the members of my lab in Pittsburgh. And finding agencies and collaboration with various institutions across the globe, including Yenamin in Kiev, whom we work on development some of the biologically active molecule. So if you do not know, where is Pittsburgh, Pennsylvania? So this is east coast of US. You see this red brick. This is the state of Pennsylvania. You zoom in. So here is what you see is Philadelphia. New York will be northern. One of the Great Lake Erie, and this is the Pittsburgh. Is actually kind of give me a Dnipro vibes. This is historically town of the steel mills, coal mines, and this is the skyline of the downtown of Pittsburgh. And Carnegie Mellon is actually a private university that's been endowed by two families, as you can guess from the name, family of Carnegie and the Mellons, who were, early industrialists about 100 years ago. So here on the left, you see this the downtown Pittsburgh. This is our campus. You see some of the sports facilities. This building in the middle is actually what's called the Historical Mellon Institute. It's the landmark of American Chemical Society, and this is the Department of Chemistry. It's currently located in my office, looks like. Now, if you're a movie fan, you might remember that building, if you ever seen Dark Knight trilogy. So the scenes on the roof and the banks in The Dark Knight Rises were actually shot in our building. So there's a very interesting history behind this building. And also, 1998, Nobel Prize in Chemistry for the quantum mechanics, actually, by John Popel and Walter Kohn. Both of them work here as well. So there's a rich history in our university about quantum chemistry and quantum mechanics. Now, I'd like to start from afar, I kind of built into it. So when you just go on the street and ask a lay person, can you imagine a chemist? You will get a response something like that. Those are strange people mixing liquids, making fumes and things like that. Now, if you Google it or ask ChatGPT, you will see people mixing colorful liquids. Now, both of these things sadly not always correspond to reality. So the modern chemistry lab is more look like that. But this is in fact not as my lab looks like. So as a computational theoretical chemist, my lab more look like this. So it's a messy desk and a computer. And we don't have any fume hoods or benches because we use mathematical simulations to describe behavior of chemical systems. And doing so, we solve Schrodinger equation to predict properties energy of molecules. And past 20 years, this field been quite growing due to development of computational hardware. Some of you might see chip like that. So there's a GPU, graphic processing unit. Some of you might game. But those chips actually behind the revolution, what's happening right now in the field of machine learning and AI, because those chips are really good in crunching numbers, vectors, and tensors. So at CMU, we also have a supercomputing center, Pittsburgh Supercomputing Center, and we host one of this machine, which we call bridges, because Pittsburgh is a city of bridges. And finally, where it is converging, and unfortunately, I will not talk about this today, but where chemistry, AI, and robotics would converge is the vision of the lab of the future, when you can imagine that algorithms, methods of AI, and robotics working together, running chemical experiment or analytical characterization through autonomous experimentation. So let's start with a little definitions. What is computational chemistry, right? So we use, again, as I said, we use mathematical approximations and computer program to simulate and calculate result relative to chemical problems. And specifically how it's done through what's called the quantum chemistry, because all molecules are small quantum objects and their behavior governed by the laws of quantum mechanics. So we solve Schrodinger equation for molecular material systems. Now, and one would piece of definition, what's called the ab initio quantum chemistry, when we solve the Schrodinger equation, what's called the from first principles. We don't use any empirical parameter or experimental data. So just doing the purely mathematical simulations. Now, you might ask, what is it good for? What it can do for you, for me? And first of all, it's very growing field because, again, computers getting faster. We get better and better algorithms and software ecosystems. But the problems that we can solve are ubiquitous. Design of known molecules, drug design, design of materials, things like medicinal chemistry, prediction of various properties, spectroscopic of molecules, materials, electronic excited state, reaction design, catalyst design. All of these things can be addressed from one or another angle using methods of quantum mechanics and computational chemistry. And why do we need machine learning here if we can solve this equation? In practice, if you ever took any PChem, physical chemistry, quantum chemistry, you might remember that we solved this equation mostly numerically because we can do analytical derivation only for small systems like particle in the box, or maybe harmonic oscillator, or very small, atomic system as a hydrogen atom. For realistic simples, we either do numeric approximations or make a lot of assumptions. And therefore, to solve this equation numerically, you actually utilize larger supercomputer systems to compute, to solve it. And very little bit. There are a couple of pieces how to solve Schrodinger equations. So what's called the Born-Oppenheimer approximations that leads to idea of potential energy surface when we separate actually, degrees of freedom of nuclei and the electrons. And then you expand it, this many electron wave functions, and you represent molecular orbitals, and you solve Schrodinger equations, and this is called the method and the basis set. Now, this is what's called Schrodinger equation, and I promise this is the only equation I'll show today. So H psi equal E psi, so this is your Hamiltonian. H, E would be your energy, psi would be your wave function, right? So under Hamiltonian, you will see a lot of different terms. When the nuclei, the electrons interact, so there's nuclei, electronic, various terms, and so forth, which you can split into potential and kinetic energy. So when you rearrange that in the Born-Oppenheimer approximation, you separate the coordinates and you solve only the electronic Schrodinger equation. And because nuclei are much, much heavier, so about 2,000 times heavier than the electrons, then we can simplify and treat motion of the nuclei classically. So you solve Newton's equation of motions, and essentially solve Schrodinger equation only for the electronic part. And therefore, to kind of frame this problem, this is what we have, is for past many years, the dilemma in our field was the following. If I run simulation of very large systems, imagine a protein or realistic material, now I cannot afford solve Schrodinger equations. Therefore, I approximate behavior of those protein or materials through what's called the molecular mechanics or classical force fields. And this is very crude approximations, where here on the left, which builds, essentially ignore a lot of quantum mechanical nature and build very simple analytical functions of, depending on chemical bonds, various angles, and non-bonding interactions. And this is what apply in what's called the classic molecular dynamics simulations. Now, if those quantum effects are important, you still have to solve Schrodinger equations, and therefore pay the price of this expense. And now where all this lead into the following picture. So here on x-axis, I have the scale of my methods. So order n, so linear scaling, quadratic scaling, and so forth, where n typically number of particles, atoms or electrons. And on y-axis, I have some kind of metric of accuracy. And therefore, we have this dilemma. If I do simulation of realistic materials, I compromise. I use cheap, what's called the force fields. Those are linear scaling methods, so order n methods. And therefore, I can afford to do the simulations for the large systems, for example, like protein, which is depicted here. And there are force fields that specifically fitted to predict certain things. But overall, the uncertainty is very high because you do very, very crude approximations. And therefore, the only way to reduce this uncertainty is to climb this ladder and include more and more rigorous description of quantum mechanics. So you go to n square and cube methods and so forth. So you go through what's called the semi-empirical tight-banded methods, and DFT was density functional theory. In the conventional sense, DFT is O(n) cube. So it's a cubic scaling with the size of the molecular systems, but you systematically reduce this uncertainty. And finally, for most of the problems of organic chemistry, this is what our interests are, is where what's called the couple cluster theory. And it's called the gold standard theory because it provides essentially a chemical accuracy about the 4 kilojoules per mole accuracy or 1 kilocalorie per mole accuracy, but you pay the price of 7 order of scaling. Now, of course, there are methods way beyond that. So if you're really into the theory, this is called what's called the full CI methods. And those are exponentially complex methods, and it's like a unachievable heaven of if you really need the exact solution for a particular system. Now, where machine learning kicks in is the following. Now, if we generate our training data using a particular approximations, in many of our works, we use the dimensional functional theory and build surrogate machine learning models. What we can do now, we teach a machine learning model to approximate these methods, and hence we can bring the accuracy and the speed and essentially train, and this is the attraction of the what's called the machine learning potentials. Now you can run much larger systems and approach the accuracy of this expensive QM calculations. That's in essence what my lab and many other labs have been doing. Now, again, probably, you know, in this school, I don't need to make this difference, but there is a clear difference what is AI, machine learning, and deep learning. So AI is a very broad term for the techniques that mimics human behavior. You know, for today, what we've been talking about mostly utilizing machine learning. So we use essentially subset of AI techniques that use methods of statistical inference. And in particular, we will use neural networks, deep neural networks, as our workhorse methods to build those models, right? So those are formal definitions. We now live in the interesting second golden age of AI, but there's certainly lots of history. And I try to relate some history here with the history of development in chemistry as well. So broadly speaking, you know, the kind of AI research emerged in the 50s after the Second World War. And then you get the golden age in 60s with the definitions, and development of perceptron hardware, which quickly led to what's called the first AI winter, where at that time there was neither scale of compute nor data. Then we see a renaissance in 80s and 90s where some of the roots of modern methods were developed, like convolutional neural networks, some of the recurrent neural networks. So CNNs, 1989, LSTM, recurrent neural networks, again, late 90s, which again led to the second winter. And what we see right now is the explosion. And this explosion is due to advances, again, further advances in algorithms, architectures, but primarily is the data and the scale of compute. And the scale of compute because we can do this number crunching on GPUs. Now, as you know, neural network is the parametric model of the brain. Now, as a chemist, what I'd like to tell you, this is very far. So the complexity of brain and complexity of human neurons is really fascinating. So this is an example of how human neuron looks like, right? So it's a very complex cell that pass the signals through a lot of chemical communication through proteins, and this neural communication happen here in the this what's called the synaptic cleft between this part, this is the axon part, and dendrite. So there's very complex chemical biology happening, and this neural impulse comes through working of hundreds of different proteins and messaging molecules and ions. And so, for example, this is imaging of two cells of the neuron from the mice. You see this passing of the signal between two cells, and look for the complexity of these two neurons, right? You see this dendrites area and how complexly it's interconnected between the cells, right? So this is real complexity of the neuron in the brain. And again, this is brain. This is a functional map of the brain of the fruit fly. And so those arrows show you the connectivity between the cells and the activation inside the brain. And you see how complex this, interconnectivity in the real the cells. Now, neural networks are very simple, I would say biologically inspired models of the brain, right? So you have the simple analytical function, right, in neurons, which typically we draw as the circle. In practice, we use very simple nonlinear function here, right? And in the classical, way how the perceptron work, you have the set of weights, this W's with these connections, and when the sum of the sets of these weights above the threshold, the neuron activates and you output some functions. Otherwise, it's zero. Yeah, so this is the classical model of perceptron. And then you stack them in layers. And you see this is the standard neural network. You get essentially layers of the neurons and look for the complexity of biology and chemistry in the real brain, right? So this is very simple biologically inspired model. Now, but nevertheless, we use neural networks because they're very scalable machine learning algorithms. Again, we use neurons as the basic processing of the units in the neural networks. We store and pass information, and train the weights inside the neural networks. Why they're powerful and useful? Because there are specifically different architecture designed to solve different tasks. And also they're scalable to massive data. Now, in contrast to traditional classic machine learning, the neural networks really can scale to terabytes, petabytes of data and billions of samples. Now, again, probably for that schools, you might know, right? So we have, you have basic neuron. So we have X, our inputs, we have Y, our outputs. So if you open this, and in the notation, X would be the inputs, neuron nodes, and the outputs. Let me see if my animation works, right? Inside the neuron, right? When you train, you have this matrix of weights multiplied by your inputs and give you the state H, and which you pass through non-linearity, some kind of activation function, give you an output. So this W X would give you some affine transformation of your input, and the F would be your activation function. Now, then you stack them into the layer. If you have one layer, this is your hidden layer, and you have two neurons, so you have, weight W1, W2, and of course, then you grow. And then this WX would be the sum of W11 and W12 plus the bias, give you Z, and you pass Z to the function and get the outputs. And the Y would be the essentially H1 and H2, so two hidden states, and pass through the function g. So if the y is your output, so this is your output function. And the way how we train neural network, right? You define the loss through, essentially how your output different from actual y's, and backpropagate and find the, the weights w. This are all those functions. Now you stack into the layer, you have multiple layer, for example, this 2-layer neural network. And then, of course, the how defined architecture, you can grow in multiple layers. So you have n-layer, deeper neural network. And certainly you can design different architecture when the number of weights would be different and independent each layer as well. So you have arbitrary number of nodes in each layer. And but what's important, so number of inputs determined by the dimensionality of your data, type of outputs, again, dictated by your problem, and everything else is actually flexible. And that's why, those architectures are powerful, because you can really design and tailor architecture. So my goal for today is to show you a little bit how this architecture been done for chemistry. And in practice, right, so neural network with a piece of code. So this is an example. We use PyTorch to write it. Now, if you think about on traditional, feed-forward neural network, now there are many drawbacks. Now, if it, for example, when we deal with images, now one of the things where, the fully connected neural networks are not very good is, imagine this situation, right? If I am making a little classifier to detect a cat. Now what happens if my cat is here? So there's 4 nodes of my 4 pixels of my image, and especially 4 connections that needed to detect the cat, right? So we use this red weights. Now, if I move a cat and my cat is here, now I need to activate these green weights. And this is not robust. And this is what's called that this fully connected neural networks do not have invariance to with respect to the cat, right? So each time when you change the position of the cat, you need to learn this new set of features. And therefore, encoding those invariances that independent on the position of your object is actually the name of the game here. Now, in images, right, as the visual examples, now there's a very high structural and hierarchicality, right? If you look at this piece of the sky here, right, you see that white pixels are, clumped together, and blue pixels. So there's a strong relationship between pixels nearby, but also hierarchicality, right? So if I take this sunflower and obfuscate this piece here and ask you to fill it, because of the structure, you can see, this is the center of my plant, this is the petals, that's the green leaf have to be here. Now, you can easily reconstruct what is missing here, because again, because of this locality and hierarchical structure of the images. Therefore, the way how to include this invariance and is, and actually when you deal with this object, right, if you rotate the sunflower, you squeeze it, you change the colors, it's still sunflower, right? And therefore, you see this preservation of invariance in images. And therefore, going from standard feed-forward neural network to what's called the convolutional neural network, that use a convolution, essentially this 3 by 3, in this example. So there's a convolutional filter that operates on the pixel of the image, produce the output, and essentially going one by one, building this convolution filter is the way to include invariance into the images. And essentially, what you learn there is you learn the weights of the convolutional filter. You know, this example is 3 by 3 matrix that produce your outputs from your from your input. Now, and this is what scientists and engineers been doing, because those convolutional operations been used in classic, image and signal processing, where those filters were actually designed by hand. For example, this is the edge detection filter, or a simple sharpen filter, which is just a fixed operation. And the goal of convolutional neural network would be find those coefficients while you train your neural network. And then, of course, famously, you stack them up. So this is the, kind of the standard convolutional neural network when you have, those stack of this convolutional layer, non-linearities, and then some kind of, aggregation, in the pooling layer. And finally, you have the classifier. Now, what we typically do, and that's again where we try to solve our problem in the supervised machine learning framework, right? So your goal of your supervised learning is, find this function, the functions that connects, in our case, molecular features to some kind of useful outputs. And here again, what we typically do is we obtain some training data, labeled examples of molecules, their properties. So you have these tuples of x's and y's. And you find the function f by minimizing, prediction error in a training set. But ultimately, our goal is to apply this function for never seen before examples of finding a new molecule or materials. And in the chemical applications, so you can imagine, right? So if you do some kind of chemical reactions or a process, you might want to have a function that, given a molecular structure, perform a solvent selections. Or a lot of things in drug discovery, we use machine learning to find the functions that connect molecular structure to find binding to a specific receptor or inhibition of specific receptor, right? So the goal of the drug discovery, we find the molecule that, interacts with specific proteins and doing certain things. Or maybe in engineering, you design a process and you find the catalysts that give you the optimal chemical and engineering process, right? This is all the goals where supervised machine learning is used for sciences. But where it relates to chemistry is actually a field, what's called the chemical informatics field, is actually has a very rich history. And chem has been fascinating actually for a long time. Can a computer learn chemistry, right? So given this simple molecular structure, can you predict, right? Is this molecule toxic? Is it useful for a particular project? What is its pharmacological profile? Can you predict various spectra and things like that? Now, and all of this kind of boils down how to represent a structure, right? So when I started, so I kind of alluded that molecules are quantum objects. So this is just an example of particular molecule. So now when molecule interacts with themselves, they look into this, and essentially the interaction governed by the principle of quantum mechanics. And this is an example, for example, of electrostatic potentials that show you, the sides of the molecules that are positive and negative, and how they would interact with each other. Now, we as a chemist typically see molecules as the sketches. So we draw the structure of the molecule and say, hey, this is a couple of rings, this is my nitrogens, and so. Now, for a computer, we often represent a molecule as a graph. Can be directed, can be undirected graph, where our atoms would be the nodes and the edges would be the chemical bonds. And therefore, we use the graph representation for computers to describe the molecule. Now, and this graph representation give a rise of very many different standards, how to represent molecules on a computer, how to save it. So for example, very typical what's called the mol file has, this is the molecule, right? So what you see here, we have the table of vertices or the nodes, right? So those are the atoms, and the table of connectivity, some of the indices of the connectivity between the atoms. This is everything would end, if maybe some Cartesian coordinates in the 3D space, right? But starting from that graph, it allows you to compute various features or use this graph for downstream machine learning tasks. And very curiously, so this is a very fun paper if you're interested in the history. So this is 1995. So Dmitry is actually a friend of mine. He used to be a faculty at University of North Carolina in Chapel Hill. He worked in the US. At that time, he worked in France. And he built a graph-based neural network in 90s. At that time, there was no Python. There was no PyTorch. So they used Fortran and essentially built backpropagation. At that time, it's actually used quotes, backpropagation procedure, and essentially done graph neural network to predict properties of molecules. At that time, backpropagation by hand. And now we're still doing that. And again, very briefly, this supervised machine learning regime and finding function F, a lot of scientists were actually doing that without calling it a supervised machine learning. So in the chemistry and cheminformatics, as in 19th century and for the most part of the 20th century, chemists and physicists tried to find this function F that connects molecular structure with biological activity of molecules, with behavior of molecules and other things, right? At that time, they've done it by hand, either crafting a simple linear equations or maybe more complicated functions. And therefore, now we have our molecular graph, and a lot of current architectures use this graph representation of the molecule and build what's called graph-based neural networks. So this kind of a seminal paper by Kip in 2016. And remember, we look a little bit as the convolution. You can think a convolution neural network as essentially very ordered graph that have grids 3 by 3 and connectivity between all the nodes essentially in this graph. And the standard convolution operation can be kind of generalized that in your convolution operator, you have the updates of your center pixels between its 8 neighbors. So your updates would be this weights between 8 neighbors and the central node itself, and therefore that essentially a convolution operation on the grid. Now, molecules are irregular, so there's not necessary 8 neighbors, and therefore kind of generalization, right? So now my graph is not on a grid, and each atom have its own different rules of valency, so you have different patterns of connectivity. So now your updates would be dependent on the number of your neighbors, and therefore kind of have this form. And based on this graph-based representations, there are multiple different ways how you build those advanced architectures. Some of them, been, simple. You can do graph and message passing. You can do, transform graph into the tensors, and therefore. Now, a couple of our popular architectures for molecules were designed in my lab, and essentially for the next half of the talk, I'll talk more specific examples. Now, the way how we do it is the following. Now, we use supercomputers to take one molecule at a time, solve the Schrodinger equations, and collect a database of molecules. So over the year, we run literally millions and tens of millions of those calculations, not only our lab, but many other. And now, given this data, and given the molecular representation, like a graph neural network, now we build machine learning model that connects molecular structure to quantum mechanical energy. And therefore, so if you're interested in more technical description, we wrote this review paper. And again, I distribute the slides so you can go deeper into the kind of heuristics. But I think, again, designing this architecture as building this Lego blocks, right? When you essentially combine the bricks of Lego, stacking into the essentially the layer, and building your architectures. Now, the kind of most known architecture in the chemistry space, this is what's called the ANI neural network. There's the paper we wrote in 2017, and that was first example when we trained this neural network for a class of molecules, what's called organic molecules, and it approximates a solution of quantum mechanics, again, in particular approximations, and give you very practical accuracy of the calculation, again, 1 or 2 kcal per mole, and about 5 to 6 order of magnitude speed up versus the DFT calculations. So whatever before was running on a large cluster and a supercomputer, now you can really run on a laptop. And the way how we encode it is to a little bit more elaborate, just a simple graph. Now, the molecules are 3-dimensional objects, so they have this the shape. So what we do is for every atom inside the molecule, we define a certain cutoff, and essentially we build this little subgraph, this little atomic kind of neighborhood connectivity, not for the full molecule, but just for this particular region. And then for neural network, you have this little receptive field. For this atom is only this neighborhood. And essentially, your neural network go one atom by atom, and the total essentially energy of the system would be sum of these atomic environments. And the way how it works, you probably have seen in every general chemistry and physical chemistry books. It's called the nearsightedness principle of the chemical interactions. You've seen graph like that. So this is the hydrogen molecule. This is the water dimer. So what it shows you strengths of your interactions and how it essentially decays with a distance. So why we can do this cutoff, because you see in many cases at certain distance, this interaction goes to 0. And therefore, this is the principle why we can build this graph only here, and we don't need to extend it beyond. And then ANI architecture is very simple. Is you take your molecule, so this is my input Cartesian coordinates. I build this little subgraphs, and again in 3D we use a little trick using what's called the radial angular symmetry function. It builds this little atomic graph neighborhoods. You pass it to a little MLP neural network. We compute what's called this local energy for every atom in the molecule, sum them up, and give us a total energy. So very simple feed-forward architecture. Overall, we maintain a software package what's called Torch-ANI. We use PyTorch ecosystems. Currently parameterize 7 elements, so you can work with most of organic molecules. If there are any chemists in the room, we use a particular approximations of quantum mechanical methods, and you can do wide variety of application with it. Do optimization of geometries, do molecular dynamics simulation, compute multiple different properties. Maybe I can do a pause here, and if there are any questions before we go deeper into the chemistry and more applications, maybe I can answer if there are any questions.
Yes, I can share the slide maybe to other participants to see all the questions.
Should I unshare?
Yes. Mm.
So there are a few questions. It was question about ML models, but then, as I understood, author of that question wrote that it was answered already. Yeah. The question was, what ML models are better for transfer learning chemistry tasks? Is there any specific requirement? But it was
okay. So I'll talk a little bit in the second part. I talk more advanced architectures. We actually do use transfer learning, and in practice, I don't think we do know what a specific architecture better or worse. But what's more important for transfer learning, how different you have low fidelity method and you have high fidelity, or high data and low data. The quality, at least in chemical sciences, is more important. What's the quality and the quantity of the data is used. Okay, I see the questions. Can this neural network work for molecules? Calculate crystals? Yes, we have periodic boundary conditions, so you can do crystals. So they are agnostic actually, and you can do materials.
14. You have 14 elements. Yeah, you parameterize 14 elements.
Yes, currently our most advanced architecture actually now have 15. So we have a first metal. Yeah, and it's a question. So my lab specifically have directions. Why we don't have all periodic table? It's just we don't have enough compute. It's just one academic lab. So periodic table have 120 elements now. The framework is generic. Our code's available on GitHub, and it just a limitations that I don't do. For example, I don't know, plutonium, uranium, and iron. And but otherwise, it's just essentially a technical problem of, for whatever applications, get your reference data and train for your favorites elements or molecules.
Another question, can we achieve better accuracy using some combinations of the computational methods, maybe even sequential?
As if I understood correctly, again, please clarify. So molecules are 3D. When you use a sequence, you actually ignore a lot of things. Sequence is very good for text sequence. For example, proteins in biology, a lot of models in biology doing sequence. But the best accuracy for molecules, you need 3D structure. So either point clouds, graphs, or things like that. Which kind of probably answers the next questions about this SMILES embeddings. We use SMILES-based embeddings for another tasks, property predictions, where there's no need for the 3D structure, but specifically quantum mechanics, the accuracy of SMILES-based model is low, again, because SMILES, essentially, what the language of SMILES doing is encodes 2D structure of the molecule. It fully ignores 3D. And different geometries in 3D have different properties and different energies, but still encoded same SMILE, and hence you lose information.
Okay, thank you.
Maybe you can continue lecture. Yeah, thank you.
Okay.
So I unshared my screen and you now can return to your presentation.
Okay. Now, speaking of accuracy, now what this allow us to do, essentially solve the problem of fast prediction of geometries, three-dimensional structure of the molecules, building this potential energy surface maps, and gas phase reaction thermochemistry. So here on the left, again, all references here, but there's a few examples of molecules where we obtain three-dimensional structure and build this what's called the potential energy maps, where you pick a couple of dihedral angles and build this essentially map with quantum mechanics and this neural network. And you get, again, the accuracy 1 to kcal per mole. You get minima where you expect to see. You get maxima, again, where you expect to see. Here on the right, actually, speaking of transfer learning, so in that paper, we use two different levels of quantum mechanics, density functional theory and couple cluster, to get exceptionally high accuracy model for gas phase thermochemistry. And specifically use transfer learning. We freeze part of the weight after we train neural network with one reference method, and then essentially fine tune and with the second. Now we build practical tools for chemists. So for example, after 3D package, start from the SMILES representation, you can quickly build three-dimensional structure. So it builds the graph of the molecule, embeds in 3D, gets a different what we call the conformation of the molecules, and use our neural network to do parallel geometry minimization and ranking, and therefore building the low energy three-dimensional structure for the molecules. Simple examples of, again, computing free energy of reactions. So, again, if there are chemists here, our free energy essentially gets you electronic term, 0-point energy, and various thermal corrections, and the entropy term. So you can directly compute it from QM. This is here on the y-axis versus neural network. Again, in the wide ranges of the energies, you get very, very nice correlation, error 1.5 kcal per mole. Now, let me show you a little piece of code. Very simple. I apologize, just did print screen from the Jupyter notebook for how simple those calculations are. So you do a bunch of imports, you read three-dimensional structure. Here it's a water molecule. You instantiate the calculator. You call, do me a single point, get potential energy. You get the value. Now you get forces if you want. You visualize, now my water molecule have non-zero forces, which mean this is not a minima. So I pick my favorite method. So for example, limited memory BFGS optimizer, define my criteria, do geometry minimization. And again, fraction of a second, we optimize geometry, get our energy and verify that forces are practically zero. And after that, again, you can do various type of analysis, compute, vibrational modes, and full featured, if you remember StatMech and Therma, you can compute all of these different terms for the heat capacity, entropy term, and overall, free energy component. And this is how you compute essentially free energy for one molecules, and from that you can compute free energy for the reactions. Right, just a handful line in Python. Very easy to do. So those things are used in globally in various academical lab, pharma companies, chemical industry, and startups. So for example, again, after 3D, simple, you do pip install, and it gets you Python library and also command line tools. So if you're interested to work three-dimensional structure of the molecules, it's available there. Now, you can do simulations not only for molecules. So this is an example of the work of my colleagues from Los Alamos National Lab that use the same architecture, but retrain it for alloy, this aluminum, and they run, using one of the largest supercomputers, they run this what's called the shockwave simulations. They train potential for aluminum, and then they essentially do study shockwave, how how shockwave propagates, what kind of defects, what interesting chemistry happens here. So again, this example of same architecture retrained with the, for example, here is a metal, and do large-scale simulation of millions of atoms. So you see they run 1.3 million atoms using 80 NVIDIA GPUs to study, again, behavior of metals under extreme conditions. Now, kind of little detour, how we train this. And can we have a measure of uncertainty? And can we tell when this model wrong or not? Very simple things. We use simple approach, what's called the ensemble disagreement. An idea is simple. Imagine if I train an ensemble of 3 different neural networks. And this is neural network 1, 2, 3. So I do a predictions, and what I can observe, there are regions where their predictions agree and disagree. Now, since our oracle is cheap, we can compute exact quantum mechanical energies. We can align this with the reference data. Now, what we see in the regions when we have good data coverage, the ensemble is usually agree. And in the regions where we have either bad data coverage or maybe no data coverage or maybe some overfit, they typically disagree. And therefore, we use this ensemble to essentially flag if the simulation is accurate or not. And we use that now because you don't need reference data. Now we can use just a measure of uncertainty to see what systems will be accurately predicted or not. And very simple example from a colleagues of mine. So this is, again, simulation of a molecule in the, let me see if this movie will work, in the little kind of aqueous environment. So you see kind of drug-like molecule in water, and they run this molecular dynamic simulation, kind of do simulation of the time evolution. Now, remember that, I can project this uncertainty for every atom. And what we can see, this one little pesky example, when uncertainty shoot up. And what we see, essentially, this is under-parametrized, and this one particular molecule adopted on physical conformation and hence have a high uncertainty. And this is the way how we use what's called active learning to train. We throw a bunch of data. We check the ensemble disagreement. If this is high, we run reference QM calculations, update the database, retrain ensemble model, and essentially this loop of the active learning, we can feed more and more data and relevant data that has a high uncertainty, and that's essentially how this databases get populated. Now, another example that was actually just published earlier this year, it's a work of a graduate student in my lab, and again, collaboration with people at Los Alamos National Lab, is to make a reactive potential for material science applications. And again, we use this uncertainty. Now we simulate molecules in the bulk in the condensed phase. And specifically, we're interested to describe what's the extreme temperature chemical reactions. So we apply things like formation of the carbon, graphene, combustion of methane, doing biofuels, and origin of life experiments. And again, this neural network and the data set actually available. If you're interested, you can grab data and models and do your own simulations. But idea is that it is transferable enough that we can do the variety of different applications for all of these different directions. So there's an example, again, what experimentally is known, and probably you might remember from the high school, that depending on the conditions, carbon form different phases. For example, it can be diamond, it can be graphite or so. And indeed, if we do simulations, we start from random atoms placed, random carbon atoms placed with different density. So we have very high density, we have medium density, and we have low density. And we do large temperature simulations. So you probe time evolution of the system. Under this extreme condition, high density, carbon form essentially diamond cubed phase, which is exactly what happened in the iron crust. Now, in the medium density, you get this kind of graphite layers, which is again consistent as well. Low density regime give us like a fullerene kind of this sheet onion-like structures, and again gets you reliable parameters for the lattice constant and other energy. And again, this is without retraining, just doing the just applications. You can do fun stuff. You can burn things. So again, interested for the energy and energy conversion. You can put hydrocarbons, oxygen, let simulation do and see, essentially how the combustion happens and consumption of molecules, formation of other molecules. And finally, we can do a kind of fun simulation. So this is the origin of life, what's called the Miller experiment, where you cook very simple di and triatomic molecules with idea how biologically plausible molecules were formed. So we've done the simulation with the simple molecules that led to formation of essentially glycine, one of the simplest amino acids. And you can study and see what's the mechanism of these formations as well. The application of these things for drug discovery. So for example, study of protein ligand interactions. Our particular neural network is not available yet for the protein part, but we can do the ligand part, the small molecules. And hence what we do right now is the hybrid simulation, where imagine this is the protein system, and this is the active site, this is the pocket. This is a database with high quality reference experimental measurements of the binding affinities, how the molecule binds to the protein. So this is the series of molecules and experimentally measured binding affinity. Now, again, as I said, we cannot do protein yet, but we can use the part of the molecule, describe it with the neural network, and the rest we still treat with the classical force fields, with the what's called the molecular mechanics. Now there is a simple, there's certain math involved, how to carefully partition the system, treat the interactions. But nevertheless, when you do this simulation and compare with 100% force field based simulations, this is what you get. Again, here on the left, just simulation using the force fields, experimental free energy versus computed free energy. Ideally, you want to be on this diagonal, have a perfect correlations. But what you can see is this ugly outliers. And again, this ugly outliers happens because of the simplification and the force fields. Now, if you replace this part, this molecular part, with the neural network, you see the picture on the right. Substantial reduction in the outliers and much larger, better correlations. Therefore, again, improving the accuracy of the simulations. Now, in the last part, let me switch gear a little bit to talk about more advanced architectures. So ANI architecture was the first. It's very simple. And you remember we use this cutoff and do the truncation. Now, if you know chemistry and physics, there are certain molecular systems that interactions go in what's called the long range. And for that particular architecture, for ANI architecture, long range is ignored beyond the cutoffs. And therefore, our next architecture is more advanced. It combined that ideas and recover a long range interaction, which is what's called the message passing, where when essentially you take your molecule and now you represent your atom would have this what's called the vector embeddings. And now those embeddings actually learnable. And you pass the messages, again, along the molecular graph to update neighbors of the neighbors and neighbors of the neighbors, hence passing these interactions. And otherwise computing the total energy with including this message passing. That gave us actually improvement into the accuracy in one directions. So this is the example. Again, Ani in blue, and actually the name of this architecture, we called it AMNet, Atoms and Molecules Neural Network. So the AMNet and T would be to how far I pass the messages. T equal 1, essentially it's equal to Ani. I essentially do interactions only within my neighbor. T equal 2, neighbors of the neighbors. 3, neighbors of the neighbors. And so this plot gives you the errors for various different tasks. And again, as you include message passing, your errors, go dramatically down. What is interesting, what we found at that time, that you don't need to pass many messages. We did this interesting experiments, how far you could pass it. But in our cases, 3 was actually optimal. That's probably dependent from the sizes of the molecules. We have the training data, because beyond 3, you essentially start learning noise, but at least it doesn't explode. But 3 was the optimal. Now we can also do fun analysis, since now every atom inside the neural network have this learned embeddings after the message passing updates. We can look at them. And so what this figures show, essentially T-SNE projectors of these vectors. And I think this is a very cool example. You see each type of atom inside the molecules cluster in their own little subclusters. You can zoom in and look for patterns of for example, carbon and different substituent environment. But it's kind of neat. This corner kind of resembles this corner of periodic table when you have grouping of elements by group and period. So you see you have oxygen and sulfur, fluorine and chlorine. So those are halogens. And interestingly, hydrogen closer to the halogens as well, which just kind of mimics the chemical intuition. So you can do interpretation of this model through analysis of this and this embeddings. Now, the final piece is that in addition to geometry, to describe the behavior of molecular systems, you need to include what's called the spin and multiplicity. For example, molecules can be radicals. For example, system with metal center have different spin states where the electron actually paired and unpaired on different orbitals. Now, and until 2 years ago, essentially all neural networks had no ability to encode spin and multiplicity. And we're one of the first to essentially design an architecture that include these descriptions. We call it AMNet2. You can read, again, the preprint. But the idea is that we add an additional input of the total spin and multiplicity of the systems. We add this additional block, which essentially redistribute the charge and the spin in the molecule and mix it with the message passing and give you, again, the total energy. This is consistent with the charge and the spin state of the molecule. I will not go into the deep details, but this building block is actually very important because it mimics what happens in real life. Let me show you this quick example. So this is a conjugated organic molecules. So you have 2 different groups on 2 ends. One is electron donating, another is electron withdrawing group. So when you either attach or detach electron from these systems, so if you look for this bottom picture, you see that electron actually delocalizes. It goes all the way through the full molecule through this double bonds, what's called the conjugation. And if you look for the spin charges, it formed the wave. You see red, blue, red, blue, red, blue. So it's called what's called the spin wave behavior. This is very known non-local effect. Now, if you don't use this spin or charge equilibration block, and no message passing. You see all the charges essentially just localized very homogeneously. You have, qualitatively wrong picture. Now, including the spin equilibration, what you see is recovery of this effect, and you see formation of the spin wave behavior. And again, this is very delicate but very important quantum effect, which is again very important to describe the chemistry and the physics of the systems. And this is why this architecture is actually very powerful to describe multiple different things. Now, you can go more deep into the physics. Since now we condition this neural network on spin and charge, we can do super fun exercise. There's a theory called conceptual DFT theory, which relates various quantities of molecules to the partial derivatives of the energy with respect to the charge. And here's, I think, the beauty of modern deep learning, because all of the neural network is differentiable. Now we can think about differentiable physics and kind of go venture into it. Now we can obtain these derivatives by interrogating this neural network and compute first and second derivatives by modulating different charges and obtain those physically meaningful quantities through the neural network, fully bypassing quantum mechanical calculations. And that all of the framework actually, it's a side benefit of this architecture. It was never meant, where we are training, and didn't include in the reference data. But surprisingly, when you compute the synthesis in practice, you get very large degree of correlation. And what is more important, although you see certain outliers, this accuracy is actually good enough for a practical applications. So there's just a quick example, again, for prediction of direction of the chemical reactions, what we call the regioselectivity. This is to what atom inside the molecules your reaction would go. So state-of-the-art quantum mechanical methods. So there's a little table, first two lines, those are expensive quantum mechanical calculation, and you get certain accuracy on the standard benchmarks. Now, if we drop in replace this quantum mechanical feature with our AMNet computed indices, all of these guys, you essentially get the same accuracy, but 1,000,000 times faster. So this allows you to do for the first time, do really high throughput prediction for the outcomes of chemical reactions in practice. And those methods are widely used in industry right now. Now, for me as a chemist, was also very interesting to see, so that accuracy of predictions actually dependent on the charge and the state of the molecules. So neutral molecules, anions, cations, and highly charged molecules essentially have the same accuracy, again because of inclusion of that important physics and description of the physics as it governs all this non-local effects. Few words about the computational performance. You can, on a single GPU, you can run hundreds of structures per second, and you can scale up for larger systems. Again, I use a protein example here just to show you the scale. So it's indeed linear scaling methods with respect to the system size. We cannot do reliable simulation as protein yet, but this is at least an example, easy example to show you the scale of with the system size. So what we work right now is to help chemists to solve the problem of localizing transition states. Now, when the reaction happens, so this is a little example here. So for example, you have reactants and products. Transition states is important. This is the kind of the highest peak, the mountain in the direction of the reaction. Now, this is what's called the special saddle point. This is a saddle point, what's called the first order. It is a minima in all directions but one, and it's a maxima in exactly one direction. And this is direction of reaction. Now, traditionally, to localize the state, you compute the second matrix of derivative, what's called the Hessian matrix. You see the second derivatives. And what we build right now is to enable neural network, essentially finding transition states and helping chemists to connect how reaction happens to build this network of the chemical reactions. Imagine if you have complex chemical systems, you have hundreds of thousands of those possible pathways. And before that was very sequential, but now we can scale up and do these calculations. So, and it actually poses a challenge, is that we need to sample, because your ML model is as good as your reference data. Now we need to sample reactants, we need to sample products, but we also need to sample along the pathway and off the pathways. So this example of extreme high dimensional problem where we have a lot of freedom and a lot of possible choices what to compute. To this direction, we actually release first data set of those reactions. So there's about 130,000 different reactions computed with the particular level of quantum mechanics that have these 3 points enumerated. You have reactant, products, and transition states. Again, if you're interested, you might find it useful. Please use it. With that, let me finish and leave you with some of the links. All of our codes available on GitHub through my lab. We have plugins. If you do molecular simulation, we have plugins for various packages. If you look in chemistry, material science related data sets, a lot of our data available either through publications or again on GitHub. Our methods again widely used in the practice, in chemistry, in drug discovery, various companies, and would be happy to answer any questions.
Thank you very much for so interesting lecture, so dense lecture. So we have some questions.
Let me stop sharing.
Yes, thank you. That's it.
Yes, code is shared.
Code is shared.
Yes, code is shared. I sent this slide deck, so you don't need to memorize the links. It's all there.
Thank you. The next question. Find if the molecular given is real effect with the neural networks.
This is cool. In the concept, what I described is there's no fake molecules. There are molecules that have high energy and will be improbable to exist. You'll just get very large, maybe even positive energy in that sense. But there are methods that actually use generative models, which I didn't talk today about any generative models. But there are other type of models that can essentially, if you properly train it, can tell you it's real molecule or not.
Okay, probably it's answered. And the last one, do we operate with reactions as with graphs similar to moleculars?
Could you elaborate, please? I don't know if person can unmute.
It's about the last slides of your lecture, maybe, where you have shown some reactions. Probably about this. Or someone can unmute, yes, and give some details.
Yeah, so I'm not sure if I understand exactly this question.
Okay, let's go to the second question. maybe we can return to this later.
Yeah, how hard is train model for new elements? Yes, so the price to pay, you need a decent cluster to enable throughput of reference calculations. However, what we see, the scale of data is not exponential. If you have more elements, it doesn't need you need exponentially more data. It's more linear. Otherwise, we would be in trouble. So it is demanding. You need a decent level of cluster or access to the to enable the parametrization. But this is not terrible.
So maybe
again, if
one
somebody interested, I'm again I don't know the kind of the audience, right? So how deep, there are how many chemists or physicists here. I don't know if my answer are too superficial or too technical. Therefore, again, if my answer is not satisfactory, send me a mail. Happy to discuss more technical if needed.
What data do we need to train for new elements? I mean, some DFT calculations, for example, or some other data.
Yeah. So typically, what you need to do, yes. So you need essentially parse outputs. You need energy forces and few atomic properties, things like charges, spins, for more advanced architectures. And then the name of the game is if you want to parameterize one specific system, right? So for example, you're interested in one kind of solid, and maybe two phases of the same solid. Then your requirements of data will be much lower. The scale of millions of quantum calculations comes if you want to make them transferable. For example, I want to describe, chemistry of CHNO, right? Because there are different combinations, different materials and molecules. So this transferability comes for millions of calculations. So AMNet2 data set right now is at 20 million quantum mechanical calculations.
So you generated all this data set in some way and then trained your model.
Yes, and if you're consistent, you have, your old data set and you extend it. You can essentially use it almost like a foundational model, right? So you have your baseline model and you can, extend it for, a particular applications or directions.
And maybe not to train some particular system, but maybe train some element. I mean, we have some element, for example, carbon, and we can add it to some other elements. So it's like a DFT pseudo potential or something like this. So when you use some files, some data for this particular element, and you can add it to any system you want.
Yes. But again, if you want to teach neural network new element, right, you need to show the examples of the new element as well. I see there's a person who raised a hand, Alexander.
Just trying whether it works. Hello, can you hear me? Yeah.
Yes.
Okay. Thank you for interesting talk. I just wanted a few questions to ask to. First, about actually, I did not get this, of course, about mechanism to take into account actually real configuration, real electron configuration. For example, Young-Taylor distortion. Could you get this Young-Taylor distortion? Do you get it in your calculation?
So if your effects are described correctly with the approximation of DFT and type of calculation you do. So for example, if I didn't include relativistic collections, relativistic effect will not be described because whatever in your reference QM data, if you do the correct calculation with DFT and it gets Young-Taylor effect, then the neural network learn it and it would implicitly reproduce it. For example, you can, if you do DFT calculation, you don't include magnetism. You will not describe it because your reference data has no magnetism.
So in the way of this solving Schrodinger equation, it is included in this sense.
Yes, yes. So if your particular approximation correctly get it, you will get it. Now, if your reference calculation is wrong, all these errors is going to be embedded inside the neural network because there's no magic here.
It's also, as far as I understand, you quite limited with number of atoms in the molecule. But when you shown this example of application of this procedure to distinguish between diamond and how it is made then, so that there are many of atoms there.
Yes, so we can again we can run. It's limited by the memory in the computer and how many you can squeeze on a single GPU or a node. You can run to millions of atoms simulation. So that basically the neural network time evaluation is a little bit more than a classical force field. So you lose a little speed with respect to the classical force field. You can run millions of atoms, hundreds of nanoseconds. So you can run very large simulations. But the training data, of course, we cannot do millions of atoms with DFT. So we run much smaller system to train it. But then in application, the system size. I think that the carbon simulations were probably 10,000 atoms. That was not a million. But we've done some simulations, for example, the aluminum example I showed.
I'm just wondering whether it's possible to get some effects, some collective effects, like charge density wave in solids. I mean that for crystal growth, how it's grows.
Oh, yes. So there's again, I'm not a material scientist, but some of my colleagues, you can do grand boundary, you can see dislocation. All of these effects, if your simulation system large enough, you can see this. There are groups that run on a very large machines. You can do hundreds of million atoms and you can see multiple grains and, you can get this. It's not macroscopic, but you get this larger effects, kind of nano scale effects.
Oh, my impression, for example, for solids, that's it's important to take into account the whole energy. For example, if you have standing waves of the electron density, something like this, is the same happens in molecular systems?
On a shorter range, it doesn't go to nanometers, and it's literally in molecular system. The scale is, whatever the conjugation. So I show you 2 benzene ring, right? So there's probably like 1 nanometer scale. So it doesn't happen on the like in solids.
Okay, thank you.
I can give a few words. Olexandr Kurdyuk is director of Kyiv Academic University. He's academician of Ukrainian Academy of Science and scientist in experimental physics. So that's why all these questions was about
pleasure to meet you. Thank you so much for coming for this lecture. I'm more into chemistry side. And so our applications mostly in molecular systems.
If there's no questions, could you define the direction? What is quantum chemistry? For example, we are speaking about quantum materials now, but what this is, I think, also became very fashionable, especially how quantum chemistry in similarity with quantum materials. What is distinctive?
I think in quantum chemistry, again, we traditionally interested in the way how to solve, right? What the exact approximation, right? What is the model Hamiltonian? How to combine these things? So more than, again, right now there's a kind of renaissance and a lot of interest in the quantum computing, which is kind of adjacent, how you can use quantum phenomena to do non-binary logic, right? So when you have a quantum bit, qubit, right? So it's not binary 0-1 state as the classic computer, but you and therefore you can describe, richer physics, solve many problems. So to my understand, so one of the directions where the interest in quantum mechanics and the quantum computing.
I mean, it's always been. I mean that any materials are quantum, but in our field now the term of quantum materials it's appeared, and it is actively in the whole in the world. Many groups appear on the investigation on quantum materials, and they or we formulated in terms of emergence, that it is some new emergent phenomena. Superconductivity is just a clear example, old example, but all emergent phenomena, which is also useful for quantum technology, something like this. But the question was in chemistry, quantum chemistry, it is still old name, or it is also something new emerging in this direction related with like
Oh, I
quantum.
see. I think where the chemistry is heading is slightly different. There are interesting properties that emerge in the scale and but chemistry, at least in kind of my realm, is going into the different. The historically chemical experiment is very laborious, very tedious, and manual tasks. So I think right now what interesting happens is, can we use robotics and AI to do chemistry experiment? Can we teach an algorithm, a machine, not to replace the chemist, but help them to be more efficient and therefore kind of drive new reactions, new molecules, and new applications. So this direction probably like orthogonal into the what's in the quantum material. Although I might be wrong, because that's kind of the quantum material is kind of far from what we do, so it might not be up to date.
It could be close to quantum machine learning or something like that.
Yes.
Okay.
Yes.
Okay. Thank you for the lecture. So
I stopped sharing of my screen because, as I see, no author appeared of the previous question. So I think we can skip it.
Yeah. So
again, if anyone interested, please follow up. Send me email.
Yeah, so if there are no other questions, maybe we can end the lecture. Thank you very much for this talk. Yeah, it was very interesting, and I will write to you then following. I have a lot of questions about the material. I had to look at the presentation again because it was too many information, and it was super interesting.
Yeah, thank you so much. And again, I apologize, I couldn't make my lecture yesterday.
Yeah, today is perfect. So thank you very much.
Okay. Thank you, everyone. Bye-bye.
Bye.
And I'll send my slide deck to Oleg.
Yeah, thank you.